Hey everyone, so today I'm going to talk to you about MRI artifacts and 3D imaging. My name is Christiane and I'm a diagnostic medical physics resident at Boston Children's Hospital. So the types of artifacts I'm going to talk about are tissue related, so these are artifacts that will show up in the image, and there's ways to mitigate them, which I'll go into. I'll also talk about motion related artifacts. These might be hard to get rid of, but there are techniques that you can use. And then there's also technique-related artifacts. Then I'll go into 3D imaging, so how to do case-based filling. If you haven't seen any of my previous talks on this, I've uploaded those videos on YouTube. It's worth watching just so you get an idea of how to fill case-based in 2D, because today I'm going to talk about how to fill it in 3D. I'm also going to do a little recap at the beginning here. Then I'm also going to talk about MR angiography. So just a few techniques, and then I'm going to go into artifacts in 3D imaging. So I'm just going to go over, as I said, I'm just going to do a little recap of my previous talks. So, if we start off with a blank slate here, this is going to be our case base. In MR, we do a 90-degree pulse, and we kind of follow that with a 180-degree pulse. So we initially tip our protons into the XY dimension. And as they are tipped, they tend to fan out and dephase, and we start to gather our signal. And sometimes they do a 180 pulse. So if you're doing a spin echo sequence, you'll do a 180 pulse, and that is because when these protons start to go out of phase with each other, if you do a 180 pulse and flip them over like this, they will start to come back in like this, and they'll refocus themselves. If you don't do a 180 pulse, then you do a gradient echo sequence. And these are things I've talked about in my previous talk. While you're doing the 90-degree pulse, you want to do a slice selection. So typically, if you just try to gather signal from, if you do this 90-degree pulse by itself and that 180-degree pulse afterwards, you're going to gather signal from the entire patient. So you want to be able to localize where that signal is coming from. So if you do a slice selection, you're basically figuring out what part of the anatomy you want to image. So it's just like think of it as taking a slice across the patient's body. Then within that slice, you want to be able to localize that signal that's coming from each row and each column. Otherwise, you just get an aggregate slice. So to do that, you turn on two different gradients, and the first is the phase encode gradient and the frequency encode gradient. So the frequency encode gradient is like the readout gradient. It'll read out and sample the signal that you get back. So when you turn on the phase encode gradient and you start to sample that signal, you add the frequencies and the signal into case base. And what you're measuring is basically, as I mentioned, so here you're tipping the protons 90 degrees like this, and then you're watching them fan out. So they're sort of fanning out and dephasing at a rate of T2 star. And T2 star is a measure of the real T2 and the tissue inhomogeneity, so the spin-spin interactions. Then if you want to do a 180 pulse, so if you're doing a spin echo sequence and you do a 180 pulse, you'll refocus them and the signal will start to grow again. But of course, after you do your 180 and flip it over like this and they refocus, they'll start to dephase again. So you'll get, your signal will start to fall off. And this can give you like a measure of the real T2. So the way that the time is set up, the echo time, is that it straddles this peak right here. And this is essentially when you start sampling the signal. And this is what we record in our image here. And we do that for each line. So we wait time TR, which is the recovery time, and this is also chosen by the tech. Once we hit TR, we come back to the first image and we turn on the phase encode gradient and sample that signal. And we do that until we fill up the entire case base. So the least amount of dephasing is going to occur at the center here. Basically, we fill up the entire image, entire case base here, and at the center we'll get the lowest amplitude, which translates to the contrast, and at the edges we're going to get higher frequency, which the edges here. And just to remind you, the precessional frequency is related to the made magnetic field B through the gyromagnetic ratio, which is typically for water it's 42.6 megahertz per Tesla. And just to remind you of the frequency encoding, so we'll read out a signal for each line here, and so we'll do a send receive. This is the received signal. Then we'll do a Fourier transform, and what we'll get from that is the signal amplitude and frequencies. So we'll get a bunch of frequencies with their corresponding signals, and then based on the frequency we can locate them in the image. And we know this because the gradient varies in a linear fashion, and the precessional frequency varies with the gradient in a linear fashion. So basically, you'll have your frequencies that map back here, and they'll map back to the respective column. So that's one piece of information that you need to know. The second part is incorporating the phase encode. So basically, after you've done your slice selection, so you do your RF pulse slice selection, you wait a little bit, and then you start to apply a gradient in the that's perpendicular to both the slice and the frequency encoding, and this will lead to some amount of dephasing. And this is the information that will get incorporated into the it'll get embedded into that received signal, and that will give you a better indication as to which row now that signal will appear in this image. Okay, so now to talk about artifacts. So the first one is susceptibility. So susceptibility is denoted by the variable chi, which I'll talk a little bit more about later. And it measures the extent a substance becomes magnetized when placed in an external magnetic field. So the precessional frequency is related to the susceptibility because it does vary the magnetic field depending on which substance is in there. So chi itself depends on the material. And the magnetic field distortions created by susceptibility effects result in variations in precessional frequency across the patient and also even within individual voxels. So one example is the liver, which is relatively homogeneous. It will have tissues affecting the apparent magnetic field even within that structure, and therefore also the precessional frequency. So these frequency changes produce, one is signal loss from the T2 star dephasing. So this is how the spins affect each other, and this will show up as a black hole in your image. We also have spatial mismapping of the MR signal. So precessional frequency is expected to change linearly with the gradient field. So when you have something that throws off the gradient, it will throw off your frequency, and you know you need the frequency to map to localize that signal within the image. So if you have something that's in the field that will disrupt that, then you might have some mismapping. So this can result in piling up of signal that's assigned to the wrong area. So this is the variable chi here, and as I mentioned, it depends on the tissue or whatever substance is placed in the magnetic field. You can think of the magnetic field as parallel lines here, as you can see. So when you add something like that's para or ferromagnetic, those terms are interchangeable. Chi will be greater than 0. And these are materials that concentrate the magnetic field, so you can see how it kind of pulls the magnetic field towards them. And that makes sense because they're ferromagnetic. And the different materials here, they have a different range of ferromagnetic properties. So air is actually not susceptibility neutral. It's slightly paramagnetic. It has a chi value greater than 0, although it's a very weak paramagnetism. There's contrast agents that produce weak paramagnetism, and gadolinium is one of them. So here I'm showing no contrast, and then you have after IV contrast, which is the gadolinium agent. You'll show some pulse pileup here. And then you have iron and titanium that have stronger paramagnetism. And so something like, a shoulder, like a prosthesis, something that's made of titanium, will show up have a stronger ferromagnetic property to it. So the chi value will be much greater than 0. Then on the other side, you have the diamagnetic materials. 0. So these materials disperse the main magnetic field. So you can kind of see here how the lines kind of flow away. So they diamagnetic, make sure that they flow away from the material itself. So calcium salts are strong diamagnetic material, probably the strongest material you can find in the human body. And this kind of shows what they look like here as in the MR image. And nearly all biological tissues like muscle, fat, brain, liver, and water are weak diamagnetic materials. So their values are still less than 0, but they have, between each other, they have very weak susceptibility differences. It's, a really strong difference in susceptibility would be a calcium salt and something that's strongly ferromagnetic like titanium. So just keep that in mind. So these tissues actually will affect each other because they're very slightly susceptible. There's very slight susceptibility, but not as much as these other materials will affect it. So just to give you an idea, of how you get a signal from a susceptibility, from when there's a susceptibility, what happens in the image. Just some of the physics. So when we place the patient in the scanner, we know that the MR signal is coming from the hydrogen proton in water. And so, you're going to have the magnetic field is going to vary depending on the tissue, and the location. But if you have something like a hip replacement or a prosthesis, like in the shoulder, that's made of titanium, or orthodontic work, like braces, this is going to alter the main magnetic field by quite a bit, as I mentioned before. And the variable chi here is actually related to T2 prime. So T2 prime is actually something that we cannot measure. We can't actually see the effect of T2 prime, but we can relate it to T2 star and T2, which can be measured. So true T2 is caused by molecular interactions, and the observed T2 reflects the true T2 as well as the magnetic field inhomogeneities. And this is this part here, the magnetic field inhomogeneities that we're going to extract with T2 prime. And we can relate it to this. We can solve for it just using this equation here. But that's really what the variable chi depends on. And, if we have an image of the brain here, and we have a calcification, and there's some water around it, the calcification is actually not a source of MR signal, because we know the MR signal comes from the hydrogen proton in water. So really, the signal is not coming from the calcification itself, but it does cause the static main magnetic field to diverge. But it's really the water that's interspersed around it that's the source of MR signal. So it's how the calcium salts affect the signal that's coming from that water. So it leads to dephasing and signal loss, essentially. You're going to have this gradient of magnetic field that's coming across the calcium salt, and it's going to cause it to disperse. And as I mentioned, when you receive a signal, basically, you do a Fourier transform, and you get frequencies with their corresponding signals, and you can map them back to the image, depending on the location of wherever these are occurring in the image itself. But if there's if the patient has braces or something like that, what's going to happen is that the frequency is going to be thrown off, and if the frequency is off, then that means you're going to map it back to a completely different location. So the frequencies might not correspond to the right location in space, and that might be an issue. So the size of the susceptibility artifact depends on a few things. So the first thing is the difference in susceptibility. So if you recall, the difference between fat and muscle might not cause a huge susceptibility artifact. In fact, their susceptibility constants are pretty close to each other. But something like fat and titanium, that will have a large difference in susceptibility. So the susceptibility artifact in that case will be affected. It also depends on B naught. So susceptibility artifacts are exacerbated at higher B naught strengths because frequency variations increase in proportion to the field strength. So we tend to avoid scanning patients with metal implants at 3T whenever possible. might want to image those patients. We also want to minimize the effect by using a short TE. And the reason for this is because we know that it's the spin-spin interactions that are causing the susceptibility. So if we have a shorter TE, this allows for less dephasing. And generally, we just want to avoid a narrow bandwidth technique. We can avoid it by using a narrow bandwidth technique. So this is some examples of susceptibility artifacts. So here you have a metallic substance in the eye makeup. This is a picture of the brain with the person's nose, and this should be an eye here. There should be some signal here as well. So the patient is actually wearing, as I mentioned there, eye makeup, and it's got some metallic substance in it. So typically what you would do is just tell the patient to go remove the eye makeup, and then you would re-image them, unless you don't care about what's happening in the eye region. This patient here has had some orthodontic work, braces, so you can see like you can't even see it at any parts of the jaw, well, the front part of the jaw, basically the mouth and the nose, so it's really affected this part of the image. So, I mean, depending on what you're trying to look for in the image, if you're trying to look at something in the brain, then this image might be fine, but if you're trying to see something in the mouth, you most likely, there's no window and leveling that can fix this. Over here, you have screws in the femur, so you can see these weird-looking holes here. Just something to be aware of. Then there's something like hemosiderin around the cerebral cavernoma in the brain, so you have some signal loss occurring here. And then there's this sort of artifact called the potato chip slice position, and this is due to a shunt that the person is wearing on their head. So it's a metallic thing that they wear, and that will kind of like cut off what should be the part of the brain on this side. So that patient is actually, this is not pathology. That person is not missing a part of their brain. They just have a metallic substance on their head, the shunt. So that brings us to the chemical shift artifact. So chemical shift is, these are small changes in resonant frequency due to different molecular environments of the nuclei. It's mainly spatial displacement of water and fat due to slight differences in the resonant frequency. So just to give you some idea about the chemistry, so for example, the hydrogen in fat is nestled along the long chain triglycerides, and those are covered by an electron cloud. And these clouds are partially shielded by fat. These clouds partially shield the fat protons from full effects of the magnetic field. But the protons in water are less shielded because their electron clouds are pulled away from them by the highly electronegative oxygen atom. So because of this differential shielding by electron clouds, a fat proton experiences a slightly weaker local magnetic field and will resonate at a slightly lower frequency than a nearby water proton. So just to give you an idea, this shift between fat and water changes as the magnetic field strength increases. So at 1.5 T, you have a difference in 224 Hertz. At 3 T, you'll see a difference of 430 Hertz. And at 7 T, you'll see a difference of just over 1,000 Hertz. And this will make a difference, and I'll explain the physics very soon. What these chemical shifts look like are basically like white and dark bands that flank across the phase encode direction. So this is occurring in the phase encode direction. You'll see why. It's basically due to mapping the signal, and this is what I've mentioned for the susceptibility artifact. So you'll see this sort of signal void here, and you'll also see an overlap of signal between fat and water here. So it's like a signal pileup. So when we place our patient in the magnetic field, we assume that B0 is static and the tissue response doesn't vary that much. So in an ideal world, this would never happen, but let's say we send in a signal and we receive a signal. The signal would be related to the precessional frequency, and it would sort of look like this, like a delta function. That never happens. So in real life, what we would get is something that looks like this, where you would have there would be a standard deviation of precessional frequencies, and you would get this sort of hump here. And this hump here is basically fat, and this at 1.5 Tesla. So, sorry, and the difference between the two is 224 Hertz. So if we increase the magnetic field strength to 70, this difference in the two here will change, and the difference will be, as I mentioned before, 1050 Hertz. So when we receive our signal, we do our Fourier transform and basically just try to map it back to where the signal should be located in the image. But here's the difference. So when we get the signal, when we receive the signal, we do a Fourier transform, and we get a list of frequencies and their corresponding signals. And the frequencies should give us an indication of where the signal is coming from. So if we have, for example, if we look at this first pixel here that we fill, let's say the bandwidth per pixel is 125 Hertz per pixel. If we keep filling in these pixels, they should all be fine because they're water. And then we get to this sort of interface between water and fat here. And we know that at 1.5 T, for example, the difference in frequency is going to be 224 Hertz roughly. So what's going to happen is this shift, because we only have 125 Hertz per pixel, we're going to see a shift, and the frequencies are going to affect each other, and they're going to basically move this signal over into the next voxel. So what's going to happen here is, because we don't have a lot of signal coming from that point, we're going to get a black line essentially, and that signal is going to be mapped here, and basically they're going to affect each other till you get to this pixel or voxel here, and you're going to get a white line because you're going to have some pulse pileup with water and fat. So this is essentially the physics behind the chemical shift artifact. And if we increase the bandwidth per pixel, if we use a bandwidth of if we keep the resolution the same but increase the bandwidth, we'll basically see all the signals with no shift at all. Because if you increase the hertz per pixel here, you're not going to see this shift of 224 Hertz unless you go to a higher field strength, because then you know that the difference, this number here, is going to change. So the range of frequencies will affect the chemical shift artifact. So when techs try to lower the bandwidth with good intentions to increase the SNR, it will also increase the chemical shift artifact, which may or may not be a problem. Let's see what they look like in the images. So you can tell that these are the kidneys here, and you can see that there's a black line kind of here, and then there's a white line here. So you can tell that the frequency encoding direction is going from left to right. And depending on what you're trying to look at in the image, this may or may not obscure the view of the radiologist who's reading it. If you come down here, you'll see a chemical shift artifact at the border of muscle and fat. So you've got this black line here. I gather that you can't see the white lines because the background here is white. You might have there's a chemical shift artifact at a junction between water droplets and silicone gel in a ruptured breast prosthesis. So you'll see these little goblets here. That's called the salad oil signs, and there's like little black lines here. So the frequency encoding direction is going from inferior to superior. Then over here you have the knee. So there's a subtle chemical shift artifact in the knee here. The frequency encoding is from left to right, and you can see the apparent difference in the cartilage shifting from the marrow fat signal. It's a little bit of it's a very slight artifact here. There's also a similar subtle artifact in the spine here, so the frequency encoding direction is being read from superior to inferior, and you can see that from there's a difference in the cortical thickness here, and you can see the dark bands that are running across. Okay, so I've described chemical shift artifacts in the frequency encoding direction. There's also chemical shift in the phase encoding direction. So the chemical shift does create a phase difference between fat and water. This is not noticed in spin echo or gradient echo imaging because the phase difference is constant from step to step. But for something like echoplanar imaging, the phase difference is accentuated, and the effect may be seen. So with echoplanar imaging, basically all you're doing is tipping the protons 90 degrees and then watching them kind of dephase and just acquiring all your data as they're dephasing. So it won't be a very good looking image, but it's fast. And so all echoplanar imaging lines of raw data are collected immediately following the single RF excitation. The bandwidth per pixel in the frequency encoding direction is extremely large, so 50 to 100 kilohertz. So if you recall, if you use a really high bandwidth, and this is bandwidth per pixel, then you won't see that chemical shift artifact. So the chemical shift artifact won't be noticeable in the frequency encoding direction. In the phase encode direction, however, the bandwidth per pixel is extremely small, so about 100 kilohertz. And it's the low bandwidth in the phase encoding direction that will translate into a noticeable artifact that may be 10 pixels in width, or voxels. So this is an EPI image with a chemical shift artifact in the PE direction. So this is the phase encode direction. And you can see the huge shift here, pulse pileup that's occurring. There's also a chemical shift of the second kind. So this is known as the India ink, or the phase cancellation artifact. It arises from pixels containing both water and fat, and it's seen only in the gradient echo, not the spin echo imaging. So you'll see, as I speak about this further, using a diagram, that the spin echo will refocus everything back into phase. So in this case, you won't see the chemical shift of the second kind because it requires these protons to be out of phase with each other. So something like gradient echo might work. Well, it does work. And this occurs in both the phase and frequency directions. So this will be seen at every point, like kind of surrounding objects or materials in the image. And the magnitude of this artifact depends on the phase cycling between water and fat, as you'll see. So if we look at this image here, basically just to give us an idea, this is the time after the RF pulse. So we've tipped the water and fat protons in 90 degrees. Now we're just watching them start to dephase, and water and fat will dephase at a different rate slightly. So at 1.1 they'll start to be kind of 90 degrees out of phase with each other, and then at 2.2 they'll be completely out of phase with each other, water and fat. And then at about 4.4 milliseconds they'll come back into phase with each other. So if we look at this image down here, and how this translates to an image, if this is a voxel with water only, and this is a voxel with fat only over here, basically they're going to be in phase with each other, and they're going to show up as bright on the image. But a voxel that's containing water and fat, relatively 50-50, maybe 60-40, once they go out of phase with each other, it's going to show up as a dark voxel in your MR signal. So if you use a spin echo technique, you might not see that because that technique tries to refocus everything so that they're in phase with each other. But something like a gradient echo they don't generally come into phase coherence at the center of the echo. So fat and water protons go in and out of phase with each other as a function of the echo time, TE. So at about 1.5 Tesla, the period of this alternation is about 1/225 hertz. This is that shift I was talking about, or 4.4 milliseconds. So at a TE of about 2.2, 6.6, 11, and 15.4 milliseconds, the fat and water are out of phase with each other. And this is specifically for 1.5 T. So these numbers can be calculated easily for 3 and 7 T. And this is kind of what it looks like. So this is why they call it the India ink artifact, because you can see all these dark lines around the different materials. So really over here you can see it. It's very, very defined. This may or may not obscure what the radiologist is trying to look for in the image, but you can utilize this to your advantage. So we have in phase versus out of phase imaging, which refers to obtaining paired gradient echo images with two different TE values. And these tissues that contain like adrenal adenomas and hepatic steatosis, they lose signal on the out of phase images, and you'll see. So just to remind you, like fat and water are out of phase at 2.2, and they're in phase at 4.4. So here's an image. These two images at the top here are showing like lipid-rich adrenal adenoma, where the arrow is. Same patient, just two different images, acquired at two different times. So this is at a TE of 4.4, and it shows, the tumor of intermediate signal intensity. And this over here is the image is taken at 2.2, so when they're out of phase with each other. And you'll see a phase cancellation artifact in this case. Then at the bottom here you have the hepatic steatosis. So in this image here, that's when they're in phase. This is a gradient echo at TE of 4.4 milliseconds. And you can see the hepatic steatosis here. So this is the liver, and this is the lesion right here. Then if you go over here to, the same patient, just imaged at a different time, just at 2.2, you cannot see the lesion here. So it does make a difference what time you image this patient. There's also the inversion recovery bounce point artifact. It's also a phase cancellation effect seen on an inversion recovery or inversion recovery prep sequence. There's a black outline of certain anatomic structures. It's not the same as a chemical shift because it occurs in T1 weighted images, but it occurs in boundary voxels of tissues with different T1 values when an intermediate inversion time, TI, is chosen. So I do talk about this in a previous talk on like pulse sequences and had to do inversion recovery to cancel out different tissue. But just to remind you, if you do a 180 pulse, basically you flip all of your protons now into the negative plane, and you basically like watch them regrow like this. So that's what you're looking at on the graph here. So you tip these protons 180, and then you wait for them to essentially, the signal to regrow. And with inversion recovery, you'll choose an inversion time. You'll select it so that it will cancel out one of these tissues. So if you want to cancel out brain, for example, you would choose a TI of, whatever this is. When brain hits that point here, you would do a 90 degrees, and basically you will not get any signal from brain at this point. You'll get no signal from brain at this point. But if your TI kind of overshoots the brain and kind of goes in the middle of the brain and the CSF or whatever else you're trying to look at, then you're going to get some signal from brain, and you're going to get some signal from CSF, along this point here. So there'll be some sort of edge artifact that shows up in the image, and it may or may not obscure your view of the image. So it might be okay, but it depends on what you're looking at. So you can kind of see those edge artifacts here and also here. Then there's metal artifact suppression. So metals have high intrinsic magnetic susceptibilities. They produce significant local field disturbances. We know that. By altering resonance frequencies, metals shift image voxels away from their true positions. And this leads to significant geometric distortions, including signal voids, like black areas, or signal pileups, those bright areas. So this is what we talked about, how metals affect the main magnetic field. And these susceptibility artifacts scale with the field strength. So one way to get rid of it is to scan at a low magnetic field, so 1.5 T, for example. You also want to use fast turbospin echo with short echo spacing, less time for dephasing to occur. Use thinner slices, high bandwidth, and parallel imaging. So with the high bandwidth, you might sacrifice some SNR, but you might get some metal suppression, which is good. Depends on what you're trying to look at in the image. Yeah, and as I mentioned, you're better off scanning the hip replacement at a 1.5 T instead of a 3 Tesla. So just to show you an example of what that suppression looks like, so this is metallic susceptibility artifacts in the spine. You can see it from the pedicle screws, and these are right here. And then these artifacts decrease with the metal reduction technique. So it might help you, actually see what you're trying to look at in the image here. So they might be needed, but it's good to know that these types of how to mitigate. It's good to know how to mitigate the effect of metal in your images. Okay, so a common artifact this is an artifact of different modalities, so it's just different how it manifests itself in MR. So for a 2D Fourier transform image in MR, there's considerable disparity that exists between sampling times for data collection in the frequency and phase encode direction. So this depends on TE and TR respectively. So for the frequency encoding direction, all 256 to 512 samples of a signal are acquired in the space of a single echo, which is TE, which is on the order of 5 to 80 milliseconds. So the TE is pretty short. This is different for the phase encode direction, which depends on TR, because if you recall, after you do a single slice selection, you turn on your phase encode gradient and your readout gradient. And basically you read one line of K-space, and you go to the next image, you read one line of K-space, and you do that, you wait TR, and you come back to the first image, and then you read the second line of K-space for that first image. So that depends on the phase encode, the phase encode direction. So in that case, a single sample is on the order of seconds to minutes, since essentially all lines of K-space have to be collected. So this is really where you're going to see the motion artifacts, is in the phase encode direction. So a useful imaging strategy for all types of motion is to simply swap the phase and the frequency encoding axes. This is not going to change the motion artifacts, but it might just, change the location of where the artifacts occur. So, for example, this is an image of the person's head. This is kind of like a slice through the head here. It's right through the eyes. You can see the eyes here, and you can see the nose. And you can tell that this person was actually blinking, as the image was being, as the data for the image was being collected. And you can tell that this is the phase encode direction, because these signals have been mismapped into different areas of the image. Now, if you wanted to flip if you wanted to swap the phase and frequency encoding directions in this case, you would get an artifact that goes along, this plane here, and also another one that goes along this plane here. So it might obscure whatever you're trying to see in the brain here. So in this case, it's fine to leave the phase and frequency encoding directions in the way that they are, because you don't really need to see the background in this case, in this image. So there's ways to reduce the motion artifacts. The obvious thing to do would be to just minimize the degree of motion coming from the patient themselves. So ask the patient to not move. Make the couch comfortable for them. MR is pretty confining, so once you get the patient in there, they can feel really claustrophobic. So they can start to wiggle a little bit, and that will cause a problem when you're acquiring the image. There's sedation, but this should only be done for highly anxious patients. The reason for that is just basically because of safety. If they have something that's ferromagnetic on them, something like that, and they start to feel burning, like a burning sensation, then they're required to call in the tech. And if they're sedated, they can't do that. So this is not really recommended. But if the patient is extremely anxious, and it's really your call to make, but I would avoid using sedation if you can at all costs. You also want to reduce the physiological motion. So for peristalsis, for example, you can reduce that with glucagon. So if you can reduce physiological motion, that would be ideal. You can also suppress signal from moving tissues, adjust imaging sequence and parameters, and detect and compensate for motion. So I'm going to talk about those. The first thing is gating and triggering. So the synchronization of gating is basically the synchronization of MR signal acquisition to the cardiac or respiratory cycle. You have prospective gating, where the MR data acquisition only begins after a detection of a desired physiological event. So in this case, if you're measuring the heart, you'll get like a pulse here, and then start acquiring images, wait for the next pulse, then start acquiring images. So that's prospective gating. Then there's retrospective gating, which is where the MR data is acquired continuously. So you're not really waiting for these pulses anymore, you're just acquiring data. And there's ways to monitor the respiratory and the cardiac cycle. So in this case, they have a pneumatic respiratory belt and transducer. So respiratory expansion can be thoracic belt, bellows, or cushion. If you're a chest breather, they'll place it across the chest. If you're an abdomen breather, across the abdomen. And this is a peripheral pulse transducer. So this is actually like placed on your finger, and it's used to measure the cardiac cycle. Now you also want to supplement that with like a fast imaging technique. So one example is known as HASTE, the half-Fourier single-shot turbo spin echo sequence. So the K-space is essentially traversed in a single train of 100, maybe more, echoes after a single RF pulse, so that 90 degrees excitation pulse. So you have the single shot and the multi-shot method. So the single shot is the HASTE/SSFSE, and it's a single shot technique. So all the K-space is filled in a single 90-degree pulse. So this sounds a little bit similar to the echoplanar imaging, but there's a slight difference in how the data is collected. So for HASTE, you go along, one row here, collect all your data, and then you go along the next row and collect all data. So you're essentially going back to, the side, so left to right. In the echoplanar imaging, you're going from left to right initially, then you go down, and then you go from right to left, and then down, and then from left to right. So there's a little bit of a difference. But the concept is kind of the same. Like you tip the protons 90 degrees, and then they start to dephase, and you just start to acquire your signal. And then there's the multi-shot technique, so the FSE/TSE, and several separate, this is when they use several separate RF excitations. So basically, they'll tip the protons 90 degrees, they'll acquire all their data, the signal will come back, and then they'll tip it again 90 degrees, watch them dephase, and collect all their data. So you'll get some variation in the contrast and also the edge definition. So this is what the images look like with cardiac and respiratory gated in MR. So in this image over here, you have ungated. So you can't see, like, this image was just acquired. It's like an aggregate signal of the lungs and the heart. So you can't see the heart. You can kind of see the lungs. Over here, you have the cardiac gated. So you can see the heart. You can start to see, like, the different lobes here. The aortic arch. You can kind of see the lungs too. But it depends on what you're looking for in the image. I'm always going to say that because the technique it totally depends on what you want to see. Over here is the respiratory gated. So in this one, you show better definition of the lungs, but the heart is still difficult to see. But if you put the two together and you do cardiac and respiratory gated, basically, you're going to see the heart and also the lungs. And I think this image is obviously the nicest of all of them, but sometimes, if you can get away with the cardiac imaging, you might as well go for it. But this image here is clearly, I think it's the best. There's also a technique called the Propeller Method. It's a radially sampled method using rotating blades composed of multiple phase encode lines. The oversampling center of K-space provides data redundancy that can be used to correct in-place rotation and translation. So basically, like every time you gather that signal, it's going to help you determine, if there was any motion that occurred that you can correct for. So this is the Propeller Method. This is K-space here, and this is how they're filling K-space, kind of like in a radial fashion. So the propeller sequence sample strips of data in a rotating fashion around the center of K-space. So there's going to be some oversampling here. And the oversampling in this region also provides redundancy of the information. So this means that data for each blade can be compared to the data from previous blades for consistency. And if the patient moves between blades, the data for the second blade can be corrected or even completely discarded based on how anomalous its central information appears. And the advantage of this method is that the center of K-space is oversampled. So this means that higher SNR, so that image will have higher SNR, which is an advantage. Another common artifact is known as the partial volume effect. This also occurs in CT. So basically you have, these structures here, and they all get averaged just in one huge voxel in this case. So, you won't be able to distinguish between this structure and this structure here. Versus, if you have a smaller slice in the image, so you get a better depiction of them. This will give you a better spatial resolution if you use a smaller slice, but you'll sacrifice the SNR. So if you recall, if you see my previous talks, I talk about how the number of protons in a voxel will translate to the SNR. So if you have more protons, if you're imaging more protons in a certain volume, which will translate to protons in a voxel, the larger your voxel, the higher the SNR is going to be. So in this case, you might have higher SNR, but less definition. And then there's also signal, like slice overlapping or interference. So I also talked about, in my previous talk, about interleaving. Basically, when you send in a signal, it's not going to look like a box. It's going to have a weird shape to it. It's going to be spread out a little bit. And it's also going to overlap with the signal right next to it, aka the next slice. So there's going to be an overlap region. So these images that are acquired, 1, 2, 3, 4, 5, they're going to have some overlap to it, also known as crosstalk. And basically these overlap signals show up as dark bands because of these overlap slices. So the protons in the overlapped areas receive double, triple, or higher levels of RF than those in the single slices elsewhere. So we tend to use a short TR because we don't use a short TR because that results in interleaving unless you're using a multi-slice imaging technique. So in this case, you have a whole bunch of images that are acquired of the spine here, and they've kind of overlapped with each other to show these huge bands in the image here. So the solution is just don't overlap the slices if you can in a single acquisition, or if they must be overlapped, do so in a separate acquisition. There's also wraparound / aliasing. I kind of stuck aliasing with wraparound because it shows up the same. This occurs when the dimensions of an object in the phase encode direction exceed the defined field of view. So you're like sampling outside the field of view, and it gets mapped back into the image. And this is a type of aliasing, so where the large phase shifts in periphery of the objects are mismapped into lower frequency shifts near the center. It's generally more severe along the phase encode axis. So, if you're trying to image the heart and you just want to see the heart, I guess naturally what you would think is, well, why don't we just zero in on the heart region here? And the field of view depends on the bandwidth and the gradient that's used. So, if you want to clip it here, you can do that, but there's a consequence to doing that just because of how you sample your image. So, aliasing basically happens, it depends on how you sample something, and the bandwidth will dictate the space between each of these samples. So, if you have a sine wave like this, and you sample it here, here, and here, basically when you try to connect those dots, you're going to get a straight line. And if you sample it here and here, you're just going to get a line that looks like this. So it doesn't look anything like the sine wave. So that's essentially, what's happening when you start to clip your field of view. So you'll get your send receive signal. This is the signal you get back from that one line of the frequency encoding direction with the phase encode embedded into it. At time t, you'll be sampling it, and you'll get a bunch of frequencies back with their corresponding signals. And if you have undersampled anything outside that field of view, what's going to happen is it's going to actually be mismapped and folded into the image. So the one thing that you really want to do, if you don't understand it, that's fine. Basically, you want to acquire all your data, and then you want to cut away at any part of the image that you don't want to see. It's because, if you start undersampling some of this data outside of the field of view, it will get mapped back into the image. You'll get these kind of folding artifacts that occur. And just to make it more clear as to what it looks like, so if this is your patient, this is kind of the you can tell this is like these are the kidneys, this is the intestinal area, and this is your field of view here. So if you're sampling outside your field of view over here, so this, this is at minus 90 degrees, for example, so it'll be mismapped at 270 degrees. So 360 minus 270 will give you 90, but it will be mapped back, the right side will be mapped back over here. And the left side will map back in the other direction. So it'll be mismapped as 90 plus, so for 450 degrees over here. So basically what the wraparound, aliasing looks like is you've got some fold over here. And you can see this is the left side that's been folded over here, and then the right side has been folded over here. It has everything to do with the sampling. So, and the bandwidth will dictate that. So, the one thing that you want to keep in mind is like, what are you looking for in the image? So here, this is an image of the brain, and you can kind of see how the back of the brain has kind of mapped to the front. And so, if you're trying to look at this part of the image, you'll be okay. If there's something you want to see at the front there, like the nose, you might have an issue. This is the side of the brain, so you can kind of see like this is the, the side of that brain here, and this is the pons. And the front of the brain has been mapped here, and the back of the brain here. So, if you're looking at, this image might be okay, depending on what you're trying to look at. Anything in here would be okay, but like the frontal lobe, probably need to increase the field of view in that case. So the simplest way, to eliminate wraparound is just to increase your field of view. Now there's always consequences. So the spatial resolution will decrease if you increase your field of view. And also your phase encode steps will also increase as a result, and that will increase the time. But again, it depends on what you're trying to look for in the image. So this is like the same person imaged with a different field of view. This is a 15 centimeter field of view. This is a 20 centimeter field of view and 30 centimeter field of view. So, what you could do is, if you really wanted to see like, the front part of the image here, you could, which you may or may not be able to use in these, definitely would not be able to use it in this image. You might have some luck here. But if you want to see, this entire front part here, acquire all the data, and then just basically chop away at whichever data that you don't need. Another artifact is called the Courdoroy Artifact, and these artifacts, they occur in K-space, and they propagate in a uniform way in the image. So the problem is it can be as small as like one little data point. So it may be an abnormally high intensity point, like somewhere where there shouldn't be one, and just gets reconstructed everywhere. So, if you have a bright point here and you do a 2D Fourier transform, you're going to see like a bunch of lines that go across your image. Now it could be a whole bunch of lines, in which case, this would be a result of the patient moving. And if you do a 2D Fourier transform, you'll get something that looks like this, with like a bunch of like static going across it. In this case, that's it. It kind of just manifests itself in that way. The good news is that this artifact is not common, but it demonstrates that there's no spatial information that you can see as far as the location in K-space. Another artifact is known as the Gibbs Artifact. So Gibbs artifacts typically appear as multiple fine parallel lines that are immediately adjacent to high contrast interfaces. These artifacts occur as a consequence of using the Fourier transforms to reconstruct MR signals into images. In MR, we're restricted to sampling at a finite number of frequencies, and this is related to the bandwidth. So we want to approximate the image by using only a relatively few harmonics in its Fourier representation. So the Fourier series is cut short or truncated. So basically, if you have a signal that looks like this, you're going to get several different frequencies, different harmonics, and if this is your edge that you're trying to look at, there's a certain point at which, the number of harmonics will give you sort of what you're looking for, but you'll have some sort of overshoot here. So this is just the Gibbs overshoot that occurs. And it does show up in the image. Sometimes, it shows up and it doesn't really obscure your view. Sometimes it shows up and it doesn't really work. But it has everything to do with the sampling. So in this case, you have a 128 matrix, and you can see in this image here, they have the Gibbs artifact occurs, and they have what is called a pseudo-syrinx. This is the spine here. And if you increase, this is at a 128 matrix size, but if you increase your sampling size to 256 matrix, you're going to see that it'll disappear. So it does depend on the sampling rate. They're a little bit more noticeable here. So this is an image of the brain kind of like cut in this direction, and you can see you can kind of see these ripples here. So they're kind of noticeable. Really noticeable on this image. This is just an image of a sphere, a little like a ball, and basically, you can just see these ripples like throughout the image. They're pretty noticeable. And then over here, you can kind of see the effect of the Gibbs artifact. It depends on what you're looking at in the image again. So this may or may not hurt the integrity of the image. Then there's the zipper artifact. So zipper artifacts are generally due to RF interference from electronic devices in or near the scanner room. It commonly passes through the center of the image and in the phase encode direction, because it affects the frequency. So it results from varying transmitter leakage picked up by the receiver system. So the door of the scanner room might not be fully closed, or its seal is defective. And sometimes the RF emission from an anesthesia monitoring equipment, like a pulse oximeter that's used on a patient, will give rise to a zipper artifact. There's also the anafact cusp artifact, which is similar, but this is due to a signal coming from an anatomy that's kind of within the active volume of the coil, but it's outside of the specified field of view. So these kind of give rise to little ghosts in the phase encoding direction. So this is kind of, you can see the difference between the two here. So here on the right, I have the zipper artifact. So this is picking up signal coming from somewhere else. The location of the signal corresponds to the specific frequency. So it's sensitive to any frequency in the megahertz range, and it kind of goes across the phase encode direction here. And it looks like a zipper, actually. So it's an appropriate name for it. And this over here is the anafact, the cusp artifact. So this is occurring, the body that's within the active field of view, but within the active coil, but not within the specified field of view. They have signals that are coming from it, and you get what this sort of looks a little bit like a zipper artifact. It's really what they call ghosts that appear in the image. And this is, across the phase encode direction. And you can kind of see the spine in this case. So then you have the central point artifact. So central point artifact appears as either bright or dark dot that's precisely at the center of the image, and it results from constant DC offset in the receiver electronics. So ideally the receiver voltage output should be 0 when no signal is being recorded, but occasionally the receiver will drift and a small positive or negative output will be present even at rest. So when the Fourier transform, when there's a Fourier transform done, this small constant offset will produce a small spike in the signal at the center of the image. So in this image here, you can see exactly where that is, central point artifact. And then there's data clipping. So improper calibration of receiver amplifier gain can result in data clipping and an eerie phantom-like image with a gray background. This occurs whenever the gain setting is too high. So the RF signal exceeds the upper and the lower cutoff levels of the RF amplifier, so plus or minus Vmax. So careful recalibration and rescanning are the only means of overcoming this artifact. So, if you try to cut off the voltage here, V plus Vmax and minus Vmax, you're going to get an image that looks like this. So you're just basically cutting off signal and truncating it. There's also data error artifacts. So it's a random glitch that occurs in the data processing chain, resulting in an image containing multiple lines that may be arrayed in a Courdoroy artifact pattern. So when I talked about those Courdoroy artifacts that occur in K-space, so these are the types of artifacts that will arise. Some of them are worse than others, though. Well, this one was kind of cool. I mean, in the image, if you're trying to, you can't use it for diagnostic purposes, but I think the lines are pretty cool. This brings us to 3D imaging. So, typically when I think about 3D imaging, I think about taking like slices of 2D images and stacking them on top of each other to create a 3D volume. This is a little bit different. There's actual ways of doing like 3D imaging where you excite a complete volume at each repetition rather than just like one slice. So it's like, instead of those thin slices, it's like one big thick slice. So you do some spatial encoding in 3D by adding a phase encoding in the third dimension in relation to the phase and the frequency encodings used in the 2D images. So if you have that huge volume, you have your phase and your frequency encoding gradients, but then you also have this gradient that's occurring in your slice selection, and I'll show you what I mean by that. So you're doing your reconstruction by a 3D Fourier transform. So like I mentioned before, what I was talking about is, you excite one image. Okay, this image here. You have a slice selection, and then you would go along and read out one line of k-space. You go to the next image, excite that image, read out one line of k-space, go to the next image, read one line of k-space, wait TR, come back to first image, read that second line of k-space, and then go from there. So basically, you try to fill up k-space for every image in that way. The difference now is that we have one thick slice, and you're just turning on a gradient in the slice encoding direction. I'm going to call it the slice encoding gradient because it's just easier to describe it that way. So instead of having this like one line here where you excite one image at a time, you just tip the gradient. So now you can get phase encoding in that dimension. Basically what you're doing is you're filling a 3D k-space. So you have your phase encode time and then your slice encode. And this is typically what a pulse sequence would look like. So, this looks similar to the sequences I've shown in my previous talks, but the difference is that now you have all of this here in the slice encode direction. So you have different amplitudes in the slice encode direction. You still have your phase encode, you still have your frequency encode, but now you've just added this component here. And what you're trying to do is essentially fill up this 3D k-space. So the exam time is now the number of phase encodes that you do, and the number of slice encodes that you do. The TR and the NEX are still there. So NEX, I explained that in my previous talks, basically the number of averages that you take, per image. That's to improve your SNR. But your exam time will now depend on the number of slice encodes that you do. So now if we, get to magnetic resonance angiography, MRA, you can use the 2D or you can use the 3D approach. Now the 2D approach, basically you're still imaging slice by slice. But here's the thing. With MR angiography, you're trying to image, blood that's flowing. And it's difficult when you try to excite one slice and then get a signal. So you do a send receive. That takes some time. So if you've got blood that's flowing, when you excite that signal here, by the time that signal, okay, so you excite that signal, goes 90 degrees, and then that blood is going to keep moving. So by the time that signal starts to relax, it's long gone. So you will not get that signal in this image here. So what they do is actually they add a saturation band. So they do a bunch of 90-degree pulses in the blood that's flowing, like in the areas before you start acquiring images, to actually get a signal from the blood. And so you do a bunch of 90-degree pulses here, so that these signals are now being tipped into 90 degrees, and they start to dephase. So when they hit these areas here, like the images, so the slices that you're selecting, you're going to see some signal that's going to come back into your receiver coil. And they do this for 3D as well. So, the difference is that now you're just turning on that gradient in the 3D, in the slice encode direction, and acquiring that image. So you can acquire it in both the 2D and the 3D. And so this, this example would be more for like an arterial flow. if you, so this would be going away from the heart. If you wanted to image the venous flow, which is going towards the heart, you would basically just switch the direction if you wanted to look at the venous flow. So instead of so you would still do the 90, but you would do them before you start imaging, as you're interested in the flow now going in the left direction. So this is what the images typically look like. This is the 2D time of flow and the 3D time of flow. So just like an example of the MR angiography. This is what the images typically look like. So this is an image of the blood flow. So there are imaging, like there are trade-offs, of course, to doing 3D imaging. So the acquisition time. So given a large amount of acquired data that's needed to fill the 3D K-space, you either have to have a very short TR or a fast K-space filling method. So the amount of signal. So at each repetition, the signal comes from the whole volume rather than a single slice that results in more signal recorded with fewer noise. So the partitions can be finer than the 2D slices because the signal to noise ratio is better compared to a slice of the same thickness acquired in 2D. The spatial resolution, so the entire volume of interest is explored with no interval between partitions, and this allows for a fine section and multiplanar reconstruction. There are still artifacts that occur because of now you have like two-phase encodings. You have wraparound and truncation artifacts that can be seen in two different directions. So this is an example of a wraparound artifact that will occur in the 3D space. So this is a 3D head MR study. The scalp, like the fat from the top of the head, this white oval, has been wrapped around and is superimposed on the tissues at the skull base. So now you have to deal with artifacts in the 3D space, and you have to be aware that they are there. So I just want to say thank you. Please subscribe to my channel, and if you like my videos, I'll be putting more out soon. And I might do an extra video for MR, maybe more on the MR angiography, and I'll take requests. So yeah, please subscribe to my channel, and I look forward to hearing your comments. Thank you.